All right, good morning. Um, this is the last lecture for this particular um, this unit. It's about water moving from surrounding areas into the roots and vice versa. So that's called water relations. All right, some of this will be a little bit of a review, but kind of wanted to go back and just hit osmosis a little bit and diffusion and things like that before we moved on to how water moves across from the areas into the plant, specifically into the roots. So, um, okay. So, molecules and ions are in constant random motion. Um, in water, when you have molecules moving around in water, that's called the Brown. That can be explained by the Brownian movement, so just particles moving in liquids. Um, so that goes for gases and liquids. Diffusion, if you remember, this is a form of passive transport where molecules move from an area of high concentration to an area of low concentration. So we describe their movement as moving down the concentration gradient or moving with or along the concentration gradient. Um, the universal water is known as the universal solvent. And if you remember, anything that's dissolved into the solvent is called the solute. And the reason we call it the universal solvent is because it dissolves most things. So the example there is sugar water. So the solute would be sugar, the solvent would be the water. Another thing I want to make sure you remember is that living plant cells are just made up of lots of membranes. So they're going to be selectively permeable. Which means that they're going to be able to move solvents and solutes across those membranes because you're going to have dissolved solutes in your vacuoles that need to go onto the cytoplasm or from the cytoplasm into the vacuole or from the cytoplasm to the outside of the cell. Osmosis, if you recall, is a form of diffusion. So it's a type of passive transport where specifically water molecules are going to move from high water concentration areas to low water concentration areas across a semi-permeable membrane. Or another way you could say is it's the movement of water from a low solute concentration to an area of high solute concentration. Again, across a semi-permeable membrane. Since this is passive, you do not need energy or ATP to move the water molecules from that high area of water concentration to the low. This will be important for moving water across the root cells. I know we talked about trigger pressure a long time ago, I think in first quarter. We were reviewing cells and things like that, but I figured we'd come back and review that. With trigger pressure, this is the amount of pressure that your vacuole exerts when it pushes against the plasma membrane and subsequently your cell wall. So when water moves into the cell, that cell becomes turgid or full of water. So nice and full and plump. And then the opposite of turgid is flaccid. So that would be, I wouldn't say dehydrated, but definitely lacking water. So when your plants kind of droop off to the side because they don't have water, those cells would be flaccid because they don't have a lot of water in their vacuoles that is exerting that turgor pressure. So it's kind of like air inside of one of those like bouncy houses. You got to have that pressure from the inside pushing all around to make that bouncy house stand upright. Same thing with your plant cells. They need that turgor pressure to be able to stand upright. So here's where the water moving in and out of the plant cells kind of comes into play. How much water comes into the cell or into the tissues will depend on a couple of things. Number one, it's going to depend on the amount of solute in the cell. Since osmosis is dependent on the amount of solute, the solute concentration is going to be important. So, if you look at the first diagram that I've got for you, showing some turgor pressure there, water is going to be, if you've got pure water, you're going to have a lot more solute inside the cell than outside. And you're going to have a higher water concentration outside. So water is going to move from that area of high water concentration to the low area. So it's going to go the higher concentrations outside the cell. So it's going to go inside the plant cell if it's pure water. So water, I know we talked about equilibrium. So your water is going to constantly move until it reaches that equilibrium. So the energy status of the water is going to determine which way osmosis goes. I don't know if you've ever talked about the energy status of water, but it has to do with how much solute is contained in that particular area. So here's where it doesn't get real super tricky, but it's very different. More than likely it's stuff that you haven't really heard of before, but this kind of applies osmosis into a practical setting, a real life situation. So because back here I was saying the energy status of the water is going to determine the osmosis direction. So you might think, what is energy status? So the energy status of water is the water potential, which, like I said earlier, is based upon how much solute is dissolved either inside the root or outside in the soil. Each area, the soil or the root, is going to be given a number, or it's going to be given that energy status number, the water potential number. So it's going to be a number. This is expressed in units of pressure because we're talking about turgor pressure here. We're referencing turgor pressure. So just to kind of give you some units here. We measure we're going to measure your energy status in bars. One bar, or you could convert that into a megapascal. What a bar is it's just the average pressure of air at sea level. If you want the conversion here, 1 megapascal is equivalent to 10 bars, or you could say 1/10 of a megapascal equals 1 bar. Kind of gives you the conversion there. Pure water is going to have the most energy potential because it's got no solute dissolved in it. Okay, so if you have any solute dissolved in it, you will have a negative energy status or a lower energy potential. So it would be expressed as like -1, -2 bars. So, and I have what the bar equals down there. So, if you look at your diagram here, we're going to look at the movement of water to and from your root first. So this, again, you're moving water. So it's going to determine which way water is going to move, whether it's going to move into the root or out of the root. So with your roots, again, water is going to move from an area of high water potential, meaning it's got low solute concentration, or high water concentration, to an area of low water potential, meaning higher solute, low water concentration. It's kind of confusing when you're talking about this high and low stuff. But this is the direction everything's going to move. Okay? Again, it's going to be across a semi-permeable membrane. With your roots, it's going to be moving across those root cells. So if you look at your diagrams, I've drawn a root there, and then I've drawn the water and the soil. So in this first picture, the root has an energy potential of -5 bars, which means it's not quite close to pure water, but it's kind of close. The soil water on the outside has an energy potential of a -1 bar. So that means that it's got more water, less solute. So high water concentration, which means in this particular instance, water would move from the soil water into the root until it reached that osmotic equilibrium. So then if you look down, I've drawn you a couple of different pictures here. So it's very crude, but you've got your soil on the far right, then you've got your epidermal cell in the middle, and your cortex cell next to it. So in this instance, it would show that you've got lots of dissolved solute in the cortical cell, medium amount in the epidermal cell, and almost none in the soil. So water would move from the soil into the epidermal cell, and then from the epidermal cell, because there's a difference between the epidermal cell and the cortical cell's water potential, with the cortical cell having the more negative number, water would then move from the epidermal cell into the cortical cell, because again, it's following that high water concentration to the low water concentration, or the low solute to high solute concentration. How this kind of applies is these last two bullets there: plant roots and excess salts or fertilizer. So the reason why this can be such a problem is if you look at that last doodle that I've got there, the root has an energy potential of -5 bars, but the soil that has maybe dissolved rock salt from, say, a winter storm, maybe now that rock salt's dissolved into the soil, and that soil water now has an energy potential of -15 bars. Well, now your root has the higher water concentration, so water is not going to go into the root, rather it's going to leave the root and potentially dehydrate the plant, which would not be good. So it's going to cause your plant roots to shrivel up and die. So with your plant roots and leaves, your leaf or your, so okay, let's talk first plant roots to leaves. Your stem has to have a higher water potential than your root in order for the water to travel up the stem. Or it's a lower. It's got to have a more negative. The stem has to have a more negative water potential than the energy potential, water energy potential. Then water is going to leave the stem and go down to the root. And that's not the way you want your water to be flowing. You want your water to be flowing up the stem. And then the same goes for your stem into your leaf. Your leaf needs to have a lower or a less negative number, or a lower than your leaf. So that way it'll go from your stem into your leaf and not the other way around. So this is kind of where that becomes important and where you can kind of apply that. So that kind of wraps up your first exam there. So hopefully everything kind of makes sense. As always, just let me know if you need any help. Feel free to email me if you have any questions. And you've got your study guide, so you can review for your test today and tomorrow, and then we'll take it on Monday. So have a good day.